var equal to 0, the orange one, in which the function is x to the power of 0, so it is a constant equal to 1, okay? Well, these are the possible examples of a power function. All power functions, independent of the exponent, pass through the point 1, 1, okay? So just to go back here, here is an example. This could be, qualitatively I mean, this is the point 1, 1, and this could be x to the power of 3 over 2, okay? And this one could be x to the power of 1/3, I mean qualitatively, passing through the same point 1, 1. And this is could be 1 over square root of x. Okay? All these functions pass through the point 1, 1. But they are very different, of course. Okay? Let me say something about the exponential function. Let me start this part. Exponential functions are the most important, one of the most important classes of functions in economic applications and in applications to all applied sciences. I mean, biology, chemistry, economics, finance. Finance is built on the properties of exponential functions, basically. And geometric progressions, elementary mathematical finance is based on geometric progression, a large part of, and finance is based on exponential functions, in which, of course, then you may have a different type, you can extend to random environments, but basically we have exponential functions and logarithms, which is the mirror image of the exponential function. Okay, so first of all, the general form of an exponential function. First of all, the general form of an exponential function is again like this, is a capital A constant, which for simplicity we take it positive, but if we take it negative, everything is mirrored by the horizontal axis, okay? So it's a mirror image. Times A is a positive parameter, which is called the base of this power, to the power of x. So what is the main difference with the power function? Both are defined in terms of a power. But in the power function, the independent variable is the base of the power, and the parameter is the exponent, like this. For the exponential function, the variable is the exponent, and the parameter is the base, which is assumed to be positive. Okay? So the main property of the power function, you remember in the linear function we studied what happens. It's very useful to contrast it with the linear function. And for the linear function, we studied what happens in terms of the increasing the independent variable by 1 unit. I want to increase the independent variable by 1 unit, okay? And I studied the change of the dependent variable in terms of difference. So this is the absolute change in terms of a difference. With the exponential function, we do the same, not in terms of difference, but in terms of the, this is called growth factor. It's not the difference between the value at t plus 1 and the value at t, or the value at x plus 1 and the value at x. but it is the ratio between the two values. This is called growth factor, okay? So if this is equal to 1.05, this means that there has been a 5% increase, okay? The next value divided by the previous value is 1.05. So the value of the dependent variable has increased by 5%, by 0.05, which is 5%, okay? So this is really important because we use exponential functions to study relative changes, not absolute changes, not differences, but ratios. This must be really important. I want to stress it. So what happens for this function if I take, suppose I could leave x here, but I like to use this as a function of time. Suppose that we are at time t, and we increase time by 1 unit, time t plus 1. So this year, next year, this month, next month, okay? By 1 unit. We want to take the ratio between the value of our variable at time t plus 1 and the current value at time t, okay? So I put t plus 1 and t in the function, in the numerator and denominator respectively. Everything can be simplified. Here, the property of the powers a to the power t plus 1 is a to the power t times a. So a, the base here, is just the growth factor per unit time. Okay? So this is its meaning. Since the growth factor per unit time is equal to a, parameter a here represents the growth factor of our function when you change the independent variable from x to x plus 1 or from t to t plus 1. It's more intuitive. In terms of time, it's more intuitive because we all know what means that price has increased by 5% or 10%. Okay? So we say that a quantity increases or decreases exponentially if it changes by a fixed factor per unit time, not by a fixed quantity, by a fixed factor. Factor is something about a ratio. Or a fixed factor per unit change of the independent variable x. So this is the basic meaning of this exponential function. This is the growth factor per unit time. In the previous example, I supposed 1.05, and I explained this by saying it is a 5% increase. In fact, this is a growth factor, but we can compute the corresponding growth rate. Keep in mind that there is a big difference between a factor and a rate. When you compute a factor, you take the variable and you take the ratio between the two values, the current value and the next value, okay? When you compute a rate, you do the same, but then you subtract 1. So basically, you subtract the current value. You take the ratio, and then you subtract 1, which is no